Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler. Today we're going to be looking at Unit 6, Lesson number 5 on variable amplitudes. This is one of my absolute favorite lessons because it really opens up students' eyes to the way that we mathematically model things in a more realistic sense. You see, up to this point in time, when we've talked about amplitude, frequency, period, midline, all of those kind of parameters that go into full sinusoidal modeling, we've always assumed that they stay constant over time. But there's a lot of physical scenarios actually where some of these parameters change. Now today what we're going to be looking at is just the case where the amplitude of a trig curve changes over time. And it's really kind of neat the way this modeling works out. So let's get right into it in exercise number 1. Alright, in exercise 1 we have kind of a classic physics scenario where we have a weight that's suspended on a spring, and the idea is that it's got some kind of resting position, maybe d equals 0. And we stretch the thing down and it bounces up and down and up and down, and d gives us the displacement that it is away from 0, where up here, believe it or not, would be negative displacements and down here would be positive displacements. That's no big deal, right? What do we know about this? Right now we're going to start by modeling it with this equation, 5 times the cosine of 2 pi t, and it says for us to sketch a graph of the displacement over 3 full periods. This is going to be pretty easy because of course we've done a lot of work now with sinusoidal modeling. Alright, so we want to sketch d versus t. Okay, we know that the amplitude is 5, so it's going to go up to 5 and it's going to go down to negative 5. I should point out that the midline here is 0, right? There's been no vertical shift to this function. It's the cosine curve, so we know it starts at the maximum. We also know that it completes one full cycle in 1 second, so we could figure that out if we needed to by using the frequency and the period and things like that. But at the end of the day, it's going to kind of look something like this, right? There's one full cycle. There's another full cycle. This is getting a little bit worse as I draw it. And there's another full cycle. And what's true, or what should have been true, is that our amplitude stayed at 5 the entire time. Now, whenever we mathematically model something, sometimes we make simplifications, sometimes we do things to just say, well, we're going to ignore this or we're going to ignore that. Sometimes ignoring particular effects is okay as long as it achieves the purpose that we really want. But there's something problematic about this, and I want you to pause the video right now and think about why this graph or why the entire function doesn't really describe the motion that's going on. Alright, well hopefully what you figured out is that if I have a weight bouncing on a spring, then over time what's going to happen is that the energy of that mass and that spring system is going to kind of die out. It's going to be what's called dampened, right? And eventually you would expect the thing to stop bobbing up and down, right? When you drop a basketball on the ground, it doesn't bounce forever and ever at the same amplitude. So what's problematic about this real-world perspective is that really the amplitude should be getting smaller. The amplitude should be getting smaller. Or the amplitude should be decreasing or something like that, right? Amplitude should be going down, but in this situation the amplitude is 5 and it's a constant. Alright, so think about that a little bit. Meanwhile, I'm going to get ready to scrub out the text. All set? Alright. So what we would like to do now is we'd like to model this in a more realistic way. Let's take a look at exercise number 2. It says, let's say we modify our model from above. Assume that the amplitude is a linear function such that at t equals 0, the amplitude is 5, what it was before, and at t equals 5, the amplitude is 0. And it says, determine a function for the amplitude of this wave over the interval 0 to 5. Notice, I'm not asking you to come up with the equation of the actual trig function. I just want an equation for the amplitude itself. So this is weird because in the last problem, the amplitude was a constant. It was 5. But now I actually want the amplitude as a function of time. Pause the video. It's a linear function. You should be able to do it. Pause the video now and see if you can come up with that function. All right, let's go through it. You know, for a linear function, we really need 2 points. What do we know? We know that at 0 seconds, we have an amplitude of 5, and at 5 seconds, we have an amplitude of 0. This is actually a very, very easy linear function to construct. Its slope ends up being -1, its y-intercept ends up being 5. So for me, there's a lot of different ways you can write it, but I really just like it like this. The amplitude is 5 minus t, right? And you can check that pretty easily. If you put 0 in there, you get 5. If you put 5 in there, you get 0, right? Now again, this equation does not describe the trig curve. It just describes the amplitude of the trig curve. Now it says determine a function for the displacement of the object over time. Well, we're going to assume here that the frequency and the period and all of that still remains the same. So instead of having a 5 out front for the amplitude, we now have a 5 minus t. And then we're going to have a cosine of 2 pi t, right? So this remains the same as before. But now the amplitude is varying. Not only is it varying, but it's doing what we want it to do, which is it's decreasing, right? It's going down. So the question now is this a better model? Does it fit more of what we think reality should look like? So in letter C it says use your calculator to graph this function along with its bounding curves over the interval 0 to 5. Don't worry about the bounding curves right now, but why don't you go ahead and put that function into your calculator. Please make sure to use the interval 0 to 5. Make sure your calculator is in radian mode, always, always, always. It should be after all the work we've been doing. But make sure it's in radian mode. Choose an appropriate y window, although our y window that we had before should work just fine, something like -5 to 5 or -6 to 6. Maybe that would be better. You know, it's not going to go any bigger than 5 or lower than -5, but that's a good curve. So take a look at that, and then in a second I'll bring our calculator out and we'll go through it, okay? All right, let's take a look at the curve. I think these look great. Aren't they kind of interesting? This is the first time I'm going to actually do a little calculator demonstration in one of these lessons, so we'll see how well I get it right. It's a little bit trickier than you might think. So here I'm going to bring out my calculator. All right. Now, of course, I'm going to put this into y1, so I'll go up and I'll enter y1. Okay, now I'll put in my function. Of course, I have to put it in terms of x, so 5 minus x times the cosine of 2 pi x, right? So get my function in there. All right. Make sure I'm in radian mode. Okay, I am. All right, let me set up my window really quick. Okay, make sure I've got x min 0, x max is 5, y min we're going to go with -6, y max is 6. Okay, it all looks good. All right, let me hit graph, and let's take a look at that graph. That's a neat graph, isn't it? That is a really, really cool graph, and it's definitely doing more of what we thought before. Now, this piece of terminology, bounding curves, right? That's a little bit new, so let's talk about that. All right, one thing that's really neat about both the sine and the cosine function is the fact that they are bounded functions, right? Cosine of anything, and it doesn't matter what's in here, is always less than or equal to 1 and always greater than or equal to -1. And therefore, 5 minus t times the cosine of 2 pi t will always be less than or equal to 5 minus t times 1 and always greater than or equal to, sorry about that, -1 times 5 minus t. So these two things are what are known as our bounding curves. So y equals -1 times 5 minus t, and y equals +1 times 5 minus t. And let's take a look at why there are bounding curves. Again, I'm gonna bring out our calculator, and we're gonna take a look at how that works. Let me now put in those two equations. So what do we have? We've got in y2, I'm going to put in, now you could distribute that -1, but I'm going to put in -1 times 5 minus t. And in y3, I'm going to put in +1 times 5 minus t. Okay, and then I'm going to graph it. All right, isn't that neat? Isn't that cool, the way that those curves just kind of hem the function in from above and below? That function can never get bigger than 5 minus t. It can never get smaller than -1 times 5 minus t. Sorry about that. All right, so that much more realistic, way more realistic, right? Anyway, I'm going to scrub out the text in a moment, so obviously, copy down anything you need to. Here we go, it's gone. Now, this of course leads us to ask a really important question. Obviously our model is better because our amplitude is getting smaller, but are there any problems with it? And in fact, there really is. It says, exercise 3 asks us, why would the model that we created in exercise 2 be problematic, especially values of time such that t is greater than 5? So now what I'd like you to do is use your calculator and open it up. Don't go just from 0 to 5, go from 0 to 10 and see what happens. Give it a moment and then we'll do it on our calculator. All right, let's take a look. Let's just go into the calculator and let's change the window. All right, we'll now go 0 to 10, and that's easy enough, and let's hit graph. Ooh, no, right? That is definitely not what we want. We definitely don't want the weight to bounce up and down, slow down and stop, and then somehow start to bounce up and down again. I mean, I don't know, maybe there's some kind of process where it would absorb energy and then start to bounce again, but not in what we're trying to model. All right, so once that weight comes to a stop, it shouldn't keep going. So let's try to make it more realistic. Okay, that's what we're always trying to do, get a better and better model. So let's take a look at number 4. It says, let's revisit the bobbing weight again. It says, let's say that we know that the amplitude is decreasing in an exponential manner. Okay, so before we were decreasing the amplitude in a linear way, now we're going to decrease the decrease the amplitude in an exponential way. So it says, what do we know about this exponential decrease? After 2 seconds, it is only 1/2 of its original amplitude of 5. So we're still starting at an amplitude of 5, but after 2 seconds, if you will, that's its half-life. So let's figure out an exponential model for the amplitude in terms of CE to the negative KT. So we're going with that continuous model of growth, or in this case, decay. Well, what do we know? We know that our C is 5, right? That's always your initial value. The question really is now, what is K, right? Well, to do that, what we're going to do is we're going to use the fact that after 2 seconds, right, we know that we must be at 1/2 of our original value. So maybe I'll just put that in, 2.5 equals 5 times e to the negative 2k. Keep in mind, I'm substituting for t here, not for k. That's actually what I'm trying to figure out. Divide both sides by 5. Of course, 2.5 divided by 5 is 1/2. E to the negative 2k. If I then take the natural log of both sides, I'll get ln of 1/2 is equal to negative 2k. Dividing both sides by negative 2 gives me the value of k. If I work that out on my calculator, not in my head, because no way that's going to happen, k is 0.347. All right. So our actual model, we'll write that over here, right, for our amplitude. Now is pretty easy. It's going to be 5 times e to the negative 0.347 t. All right, so let's take a look. Our actual displacement, right, will be our amplitude, 5e to the negative 0.347 t, times the cosine of 2 pi t, right? So that is now our new displacement function. Remember, what we're coming up with in A is only the amplitude, right? This is our A. So Yet again, we want to use our calculator to see how good this is, and we want to go back to that original window of 0 to 5. All right? Original window of 0 to 5. So take your calculator. This is going to be a little bit tricky. Put this function in. Go back to your original window to 0 to 5 and take a look at what it looks like, and then we'll take a look at on the computer's calculator. All right, let's do it. So we're going to go back into the calculator, go back into y1, clear that out. I'm going to clear out the bounding curves. I think maybe I'll put everything in at once, and we'll take a look at the bounding curves. Let's see, in y1 I'm going to put in 5e raised to the, be careful here, negative, don't use subtraction, negative 0.347 t, well, x, close parentheses, times the cosine of 2 pi t. All right, let's talk about the bounding curves, right? For the bounding curves, what I'm going to be doing is I'm going to be just replacing this quantity with a -1 and with a +1, right? So in y2, I'll maybe put the -1 in, so that's going to be, whoops, that's the bell. Don't worry about it, everybody. We all know what that means. So one of my bounding curves is going to be y equals -5e to the -0.347t. And one of them is going to be +5e to the -0.347t. So put both of those into my calculator. Again, this will take a little bit of time. We just got to be patient, make sure that we put it in correctly. 5e to the -0.347t. Enter. All right. And now we're going to hit graph. All right, look at that. That's a lot better, isn't it? Right? And in fact, if we opened up the window right now, and I encourage you to do that, maybe go 0 to 10, what we're going to see is that we're just going to see that amplitude getting smaller and smaller and smaller. Right? In fact, it says determine the limit of d of t as t goes to infinity. Well, for this, what you end up using is something that we haven't talked about in this class yet, which is what's called sandwiching. And like literally, anyway, 5e to the -0.347t times the cosine, maybe if I do it really fast, of 2 pi t is less than or equal to 5e to the -0.347t, right? That's our one bounding curve. And this is our other bounding curve. Now, because this curve is between these two, if I can figure out what the limit of these two are as t goes to infinity, I can maybe figure out the limit of this. Now think about it. Both of these are decreasing exponentials. And as t goes to infinity, this goes to 0, and this goes to 0. And because they both goes to 0, the quantity in the middle also must go to 0. Right? It's what's called sandwiching. If I can trap a curve between something on top and something on the bottom, and they squeeze or sandwich that curve together, then I can also figure out where it goes. And we're going to see that a little bit later on when we look at the derivative of sine and cosine. Anyway, sorry that that took me so much time, and sorry that we lost all the text. I'm going to have to figure out what was going on there in a little bit. Anyway, why don't we finish up this lesson? So, even with that blip at the end, thank you for joining me for Unit 6, Lesson number 5 on variable amplitudes. Maybe if I'm lucky, I can cut some of that garbage out. So anyway, until next time, remember that you can always find the lesson, a link to the lesson, and the homework for this by clicking on the video's description. Until next time, I'm Kirk Weiler. This is Arlington High School Math 4 Honors. Keep thinking and keep solving problems. Bye-bye for now.